Welcome. This is an update on something we have started last time. The topic is natural groups. Groups which are determined by a metric space. So if you have a metric space, this is called natural if there exists a unique group structure on it, such that every group operation, left or right multiplication or inversion, is isometry. And so this can then be upgraded to a metric group. And we have seen examples. So finite groups of prime order. They are natural, so because we can just find a metric space. There's just one group structure, so that's things. And we have also seen R. R is natural, so that is with a, so we can take this metric space, and there is only one group structure on this, such that all translations are isometries, or T. Or we have seen cyclic groups in general not, but the dihedral groups. Talked last time a couple of times about Diatic, so Diatic is on my mind, but that will be the topic today. The dihedral groups, finite dihedral groups, or then the infinite dihedral group. That's just a finitely presented group such that a square is equal to b square is equal to 0. So this is, and of course you can ask what groups are natural. I wonder whether the Diatic group is, and just to illustrate what I said last time about the stack exchange, you look it up and you ask that in Google and you see that the group of all isometries of the Z2 is huge, and but it doesn't give you a lot of details. So you look up papers, and there is a paper of Bishop which gives that. So it's a huge group, and so it's much larger than this group. And so the answer is kind of really write this down, whether there is not some kind of strange metric which makes it natural. So I still don't know. But what I was thinking a bit more about is the Diatic group, and it's something I was thinking about since 30 years. When writing my thesis, I got naturally to the Diatic group of integers in the context of ergodic theory. Let me just tell you a little bit about the Diatic group, how I know the Diatic group of integers, and so that will be the second part. So in my thesis, I was working on ergodic theory. So we have a dynamical system. And you can look at random operators, random variables on that. So this is a random Jacobi matrix. Random. Can be just defined by this dynamical system where the entries are given by stochastic processes. And what I wanted to do is I wanted to factor it. So I wanted to write the operator kind of like a Dirac operator. So D is a Dirac. Think about L as a Laplacian. T is a Dirac. And what happens is, what you have to do is, in order to achieve this, you have to take this dynamical system, which is here given on a space, and you have to double it. So make an integral extension. 2 to 1. So we make a double. We take a copy of the x, and then we just take a new system which goes up and then takes t down. So we kind of double the map. So that's what we call the phi of t. So it's a double. So we take 2 copies, and so phi of t is the kind of integral extension. And what happens is this has a unique fixed point. In the space of automorphisms of the probability space. So this is a Lebesgue space. Every probability space, reasonable probability space, is a Lebesgue space. So we actually can write it like this. And then what happens is, this is a von Neumann. This is von Neumann. Kakutani system, and you can just compute the spectrum of the corresponding Koopman operator, the spectrum of f goes to f of t. It's a unitary. Is this Prüfer group? These are so it's all the e to the 2 pi I k over 2 to the n. So these are then Dyadic rationals. And so the spectrum is that, and then by general principle, this Prüfer group is P. T infinity, let's just call this T infinity. T infinity, this von Neumann-Kakutani system, is a group translation on the dual group, and that happens to be the Dyadic integers. The Dyadic integers. So, and it's actually just the addition, it's the adding machine. X goes to x plus 1. What is very nice in this Dyadic world, so there's the real world, there's the Dyadic world, and everything is very similar. Here the quotient of r over z is the circle, and here if you take the Dyadic rationals and you take the quotient over, you take a quotient and you get the Prüfer group, and the dual is the Dyadic integer. So in some sense the Dyadic integers play the role of the circle, and the translation which you have here, x goes to x plus alpha. There's no smallest translation on the circle, but here there is the smallest translation. The smallest translation there's a unique, there's kind of like a Planck constant here. So this is very nice in this respect. There's the smallest translation. So smallest translation. So I should mention Oscar Lanford. Who was my advisor, and I learned dynamical systems from him. And actually Dyadic integers, or the dual of the Dyadic rationals, is called the solenoid. Maybe I just show you a picture of that solenoid. It's a very nice system. So So if you look at the solenoid or dynamical system, solenoid, it's the attractor of the map z omega goes to z square, and then it's a strange attractor, so it's a fractal and has positive sensitive dependence, has sensitive dependence on initial conditions. So already has been considered by Smale, and then came all this theory of strange attractors. And maybe I'll just show you a picture of this solenoid. It's a very beautiful thing. So you start with a donut, and then you what happens is you wrap it, it wraps it around, it becomes smaller and expands and doubles it. So here it's kind of just after two of these operations, you get 4 loops here. So if you take a cross section, this looks then like that. So you have 1. So after 1, then you have after 2 iterations you have 2, and then again you have 2, and so on. So it's kind of a self-similar thing. And actually this is Z2, the Diatic group. So you have just to put the group structure on it. So it's a Cantor set. So it's a compact but completely disconnected set. So it's very interesting that here in this context of ergodic theory, you can naturally do this Dyadic group of integers. And what you have is kind of usually how you write Dyadic integers. You write them as x is equal to 0.A1, A2, A3, A4. So the AK is in 0, 1. So it's kind of an infinite sequence. There's another thing, you can write it as AK, P to the K, Q to the K. So that's another way to write it, so that you have actually the integers are part of the integers are part of the Dyadic integer. Dyadic rationals, by the way, are just one-to-one. There's an explicit map which maps the rationals to the Dyadic rationals, and that's the question mark function of Minkowski, which I recently tweeted about. So this is one way how you can write Dyadic integers. There's another way. What you can do is you can actually write them. So if you take x as the sum ak 2 to the minus k, then what you have is k is equal to 1 to infinity, and this is in the interval 0, 1. There are some problems problems, which is, from the ergodic point of view, it doesn't really matter. But what you have is this if you write down the t infinity, for Neumann-Kakutani system, this is actually kind of an interval exchange map with infinitely many intervals, and so this is measure preserving. So it's piecewise measure preserving, but that's the way how you can deal from an ergodic point of view. It doesn't matter, these points here are countable, so they don't matter from an ergodic point of view. But that's one way also how you can kind of see the Dyadic integers just as part of the interval 0, 1, even so there is some identification problems at the 2 to the minus n. But that's the way to actually represent them nicely. So every time you have to choose, you have to make a choice, 1, 2, 1, 2, 1, 2. And so what you actually get is, this is naturally also the Julia set. These are kind of Julia sets of disconnected Julia sets when C is outside the Mandelbrot set, are actually such Cantor sets. And that's another place where I kind of got into that. what happens when you do this operation again and again, so when you take the L and then you get the D, phi of L is equal to D, and you iterate this thing, you get to a Jacobi operator L infinity, which is over that it's almost periodic. Just because it's given by a group translation of a compact topological group, so you have that fixed. And what happens is, so the spectrum of these operators L infinity, this is kind of on the Julia set. So that's kind of was one chapter in my thesis in 1993, that you have kind of, you iterate the quadratic map in space of operators. And of course what happens is the spectrum of D is just related to the spectrum of L by taking the square root of L minus C. And this square root always doubles things, so that's what you do. You double, and then when you repeat it again and again and again, you get in the limit. You get to it's an attractor it's an iterated function system in the space of operators. So then you have a limiting attractor, and then you have a group translation on it, and the map itself is just a doubling map. So that's a shift. It's a Celtic map, and that's the map which actually is induced by the quadratic map x squared plus c on this Julia set. So you see here kind of the Mandelbrot set. So if you're outside the Mandelbrot set, then the Julia set is completely disconnected. It's a dust. So actually these are not examples. You don't see, usually you don't display even the dust because the dust is not visible. It's this counter set, but maybe I'll show you an animation with XAOS, the program which allows you to see Julia sets and dive into the Mandelbrot set. So that's kind of how I got into the Dyadic group of integers. But so it's a very nice thing. It's a compact space on which you have a smallest group translation, and it naturally appears just as an attractor of a doubling map. So this doubling map is something which kind of looks like you look at the 2-to-1 doubling map, which is also in geometry appears often. It's kind of like a fiber bundle with the C2. So that's that gives you then this naturally these Dyadic integers, and this is just a unit disk in the Dyadic, in the field, Dyadic field, which a 2-adic field, which is the completion of the rational numbers with respect to the 2-adic valuation. So this is a very natural field, and there is a theorem of Ostrovsky which says that you have only the completion R, or you have the QP for prime P, and Q2 is the smallest one. So it's a very, very beautiful world. Completely different world than the real world. It's kind of a nice blog entry by Tao. Maybe I display that quickly here. So which shows how many different ways you can look at this these analogies. So this is part 2. Actually part 3 also, to see that. So that's maybe 3. Is how to see this Dyadic group of integers. I think when you look at the Julia set of a parameter which is outside the Mandelbrot set, then you see it. It's a counter set. You can also see it with this solenoid picture here, which is so Oscar Lanford was a big fan of this strange attractor, and so it's a classical topic in become a very classical topic in dynamical systems theory. And now it comes to something which I just explore right at the moment. It's maybe a little bit fresh. I don't know whether it really will work out, but let's look at that. Okay, let me just start with what we have looked at last time. Z is not natural. And the reason is there is another group structure on Z. It carries another group structure. And I call this the half integers. But maybe I just call it now 0 prime, which I called 1/2 before. So there's another copy. And what we do is we just keep on Z, on this other copy, we have time reversed. We have a symmetry which is going between the two branches. And so A goes from, so this is C prime, just a copy of Z. But the 0, there's only one 0 element, so we build a new group structure by taking, we call A, and then we call B this map here. So when we look at that, so AB, so A square is the identity. And then we have B square is the identity. And in order that this is so what we can say is T is equal to AB. On the Z, and is X goes to X minus 1 on Z prime. So what we have is we have a new group structure. Is equal to B squared equal to 1. This is the and it's obviously you can realize this on the integers again. So what I did last time is actually I just took this and then I took this 1/2 and 1 and then 3/2, 1. So what happens is you can build a metric space here. You can build a metric space such that you can realize every point in this metric space you can realize as a group element. This is the A, this is AB, this is ABA. And so this is 0, this is B, this is BA, so this is BAB, and so on. So you can build this other group, and with this metric, if these distances here are different, what happens is if these distances are different, then this is a metric space. Defines your metric space such that now X plus B plus 0 has a unique group structure. So the Diadic group is natural, while Z is not. So now, but this construction of new group, so what we have is we have constructed from Z, we have constructed a new group, and this can now be done on any group. So on any compact metric group. So I assume now that X, B plus 0 is a compact metric group. Actually, I assume compactness so that we have a maximal diameter. So in this case, in the discrete case, it also works if you have a smallest unit. We just want to make sure that we have it actually works even in more general. It works even on R if you have no discreteness. So the compactness is not just for convenience, so that we have a smallest, so we can really build a clear new group. So what we do is we take this group G, and this group has a 0 element, and what we do is we do exactly the same than here. We can just take a copy of this, and on this copy everything is reversed. So the operations are so there's a 0 prime here, and so there's an involution which goes forth and back. So what we do is then we have the translation here. This is the translation Tx. Tx is A times Bx. And what happens if we take it here on the other branch, we have A Bx. We are going backwards. So you see everything. The Tx operation gets you from -x back. The group translation in G is now any group translation is now a product of two involutions. I should mention here maybe my geometry teacher Max Jäger. So geometry 1 and 2, I found it at that point too elementary, but I appreciate it now. He was putting everything on the footage of Spiegelungsgeometry, of geometry of reflections. So what you have is kind of if you have reflections at one point and then a reflection at another point, so what you get is you get translation. So the Tx, and this is the reflection at A, and this is the reflection at P. So reflection at A times the reflection at B is a translation. So that's the nice thing. So you can kind of think about the reflections as points. So that's just an analogy, which is so that you can build up everything. All the group translations are now products of involutions. Like here, everything is a product of involutions. So in this case, we have realized that the number line, the integers as this finitely presented group, which has two generators. And here also every group translation can be written as a product of two involutions. But now what we can do is we build a new metric. Phi d on phi of g. And so what we make is just that we make this distance just maybe larger than any distance you can have here. So that's kind of something which kind of then will force the group structure. And now that's the proposition which I want to actually do, which is quite fresh, but I don't yet know whether this is ready. So this is the proposition. If G is natural, then the double cover phi of G is natural. Now what we have to do is we have to show that there is only one group structure on this, and one can do that. So there's only one group structure on this union here, such that every translation is an isometry, and every also reflections, also inversions are isometries. So what happened here is the what happened is that the isometric group was actually just a dihedral group, and so because it was the infinite dihedral group, and so it has to be a subgroup, and the only subgroup which we had is C, but C is or C2, and they are you know, strictly contained. So this is a non-abelian group, and this was an abelian group. So in this case, we don't assume that G was abelian. This could be any group, and what we have is now we have a new group structure. So I wrote down here the group structure, and we have to show that this is the only group structure which we can build. So if we take two elements here if we just stay here in G, so what happens is if you take out two elements here, we stay in G. So this is a subgroup, and on this subgroup we have only one possibility. So that's just by assumption, because this was not natural. Also here, what happens when we take the group operation here, what we do is we actually, when we take two elements here, we go back here. If we take a group element here and a group element here, we go here. And the question is this really kind of the only group structure which we can build? Show that phi is a contraction. There's a natural metric which has been introduced by Edwards, and it's called the Gromoff-Hausdorff metric. And so then you would, by the Banach fixed point theorem, you would have a fixed point. Verify the fixed point is G infinity. Verify G infinity is natural. And what I also think is true is that G infinity is the group of isometries. Dyadic group of integers, which is much larger than the Dyadic group of integers itself. What you can do is you can define it on integers. And then extrapolate to Z2. So because they are dense, so the integers are dense. The integers are just all the sequences where after some time you have 0. And so these are 0, 1s. So this is an integer, so this corresponds to the integer sum ai to the I. But then you can complete this, and you get the Z2. And actually that's what the adding machine does. So when you add, so P, so this makes 0, 1, 2, 3, and so on. So this is dense in Z2. It's actually uniquely ergodic. Minimal. Minimal means that every open set will be visited, and so uniquely ergodic means there is only one invariant measure. That's the Haar measure. Okay, that's it for today.